All right, hey everybody. So I am going to do a very quick video that is going to talk about transport protocols related to the topic that we were talking about last time on the first question of the homework. So let me share my screen. All right, so I'm going to go use Microsoft Notes here and draw a few things. So we've seen something like this in the past, but this is what I was referring to in terms of a visualization that we will use repeatedly when talking about transport protocols and TCP eventually. So typically we'll have a client. Oops. Protocols. We have a client here. We'll just call it a server. Usually the distinction between a client and a server is who starts first. So the server, sort of by definition, needs to be running. And then the client pops up and is the first to interact with the server. So that's where we sort of pick things up. Let's draw a time dimension. So time is going down. We'll say this is time t0. And let's say that time t1 is related. T0 is the time when the first bit of the frame that the client is sending. So we'll say we're just going to talk about a very simple, like a UDP ping application. Okay, so the client sends a message, the server receives it, and then echoes back either the entire message or maybe just echoes back an acknowledgement. And that's actually what we'll draw here. So the size of the message will be different in either direction. All right, so the time t1 minus t0, we'll define that as the transmit time, or tx time. So that's the time it takes to send all the bits out on the way. And that tx time, one way to derive it would be the number of bits divided by, I think the book uses R for the rate. So it's the sending rate that is associated with the link. And tx time, the units are obviously in seconds, and we like to deal with times in units of seconds to a precision of microseconds. So like 0.00080. All right, and now assume that the client and the server are located across the country from each other. So the client, let's say, is in New York and the server is in California. The time it takes for a bit, or it's really going to be a impulse of electromagnetic energy or light, which all travel roughly at about the speed of light. And speed of light sounds like it might be fast, but that actually corresponds to a one-way delay or propagation time from coast to coast of roughly 30 milliseconds. Okay, so I'm going to draw transmission time as observed by the server. And so let's call this time T0 prime, this time T1 prime. And so again, T1 prime minus T0 prime better equal Tx time. That does not change. But the time T0 prime minus T0 is, think of the answer, propagation delay. I'll just call that the prop delay. Okay, and then at T1 prime, the server has received the frame, and then there will be some processing, some overhead before the server does what the server application or transport protocol does what it's supposed to do, which is either to, if it's the ping application, it's going to reply, echo the received message. If it's a more like a transport protocol, which is what we're talking about, this message gets to the transport layer in the stack, and the transport protocol will issue an ACK. So that says that the data contained in this message needs to have a sequence number. Okay, and so our client will, whenever it sends a new message, it's going to increment the sequence number. We'll look at the format of this message in a second, and it'll correspond to what we're going to work with in the programming question of homework 1 and sort of continuing on from there. So just imagine in your mind the client is going to send messages starting with sequence number 1, then 2, then 3, and the server, if all goes okay, will issue the ACK. Okay, so can't draw a straight line there, but it's really two sort of parallel lines that reflect the start and stop of the transmission. And it's relatively smaller in time than the client message, because the ACK is only going to contain a header. It's not going to contain the application data of that was in the client message. Okay, and so we'll call the start and stop, we'll say T0, T1, T2, and T3. So T2 is the first bit of the ACK, last bit. And at the client, there's T2 prime, T3 prime. So T2 prime minus T2 is going to be the prop delay for the direction shown by that arrow. When the client sends to the server, the prop delay is in that direction. Unless otherwise told in any problems that we look at, you can assume that the prop delay is the same in both directions. And also, unless I tell you otherwise, you can assume that the rate or the available bandwidth or the throughput available to the client and to the server is the same. Okay, so the time interval of T3 prime minus T0 represents the round trip time. Okay, so that's like in ping, you issue a ping, and that's what you see is a number of round trip times. What ping, the program, does is issues, it just does multiple iterations, where an iteration is, and sometimes it's called an epoch, it's a period of time where activity work is done, and then it repeats over and over and over. Okay, and in this example, the work done in an epoch is a transmission from the client to the server and a transmission from the server to the client. The other important time that is of interest to us is going to be the one-way latency. So the time it takes for this packet sent by the client to be received by the server. So that would be T1 prime minus T0 is the one-way delay. Okay, and in the ping program, and also in our UDP echo program, which is trying to emulate ping, we have a parameter that defines the iteration delay. So that's the time before the next iteration. So this would be the iteration delay. And just to let you wrap your hands around numbers, so if we do a round trip time between machines that are located in Clemson, for example, we'd see, well, on the order of 1 to 2 milliseconds, depending on where you're at. If you're on campus, if you're off campus and ping a on-campus machine, you might see a round trip time of 10 to 20 milliseconds. And the default iteration delay is typically 1 second. So the iteration delay is huge compared to the round trip time. So this is definitely not drawn to scale. In our discussion here, we're talking transport protocols. So it's has a totally different purpose from ping or our UDP echo program that tries to emulate ping. The purpose of those programs is to sample the round trip time between the client and the server, and to also estimate the loss rate that is in effect over the network. So let's talk about loss. Oh, snap. All right. Need to redraw my. Uh-oh. Okay, why is that not working? Interesting. Why would a pen stop working? All right, I think I got things fixed here. So added to the picture a bit, we now see our transport protocol, whose job is to send one message at a time forever. Okay, and so this is referred to as a stop and wait protocol. And we've defined that term epoch, which is time interval that will be repeated over and over again. So the work performed within a time interval that's repeated over and over again. So right now, the work that's being done in an epoch is it's going to send one message. And the time it takes to send that message is going to be an RTT. So if we wanted to consider the throughput of this stop and wait protocol, and this equation is going to be applicable for all conversations today here, talking about transport protocols, it's total data sent in an epoch divided by the time, the RTT. So since there's one transmission and then we stop and wait, we'll say, well, first, obviously it's clear even from this figure that the client could continue sending. So it could send the next one immediately, right? So it send 2 consecutive messages. So this gets us to the concept of a window. And a window is, we'll define it as the number of messages that will be sent each epoch. And we can define a window to be in units of bytes, which is what TCP does, or we can simplify and say the window is in units of messages. So we'll just say units of messages. And so big picture for this transport protocol, sort of put it in a separate box here. One example, concrete example is, let's say that there's a file at the client. And let's say it's very big, like 10 million bytes. And we have a application that creates a UDP socket, and it's going to effectively send that file in tiny little pieces, which are the messages. So let's say that the message length is 1,000 bytes. So to send this file, if we are sending 1,000 bytes at a time, let's see, so it's 10 to the 7th large, and if we send 1,000 bytes, that would be 10 to the 4th iterations. So it would require 10 to the 4th iterations to send. And this is at the receiving side, and this app, maybe its job is to receive that file. So basically the application is a file transfer. All right, so I've added a bit to our drawing here. Last thing I talked about was this additional box here that was describing a hypothetical application that used our transport protocol, which currently is a stop and wait. What we want to consider next is what happens if a packet is lost. So this is the reliability aspect of the transport protocol. We'll assume that we want a reliable protocol. And so again, this now moves us drastically away from ping and from our UDP echo example program. So this is a transport protocol that is intended to transport real application data to a receiver, and it needs to know with 100% certainty that the data has been transferred. If for example, the client message tagged with sequence number 101. So in other words, let's say that we've been running for a while and we reach a point where we send the 101st message. A loss event is defined as either the message or the ACK has been dropped, right? Because in either case, the client has really no way to differentiate between which one has been dropped. And so that means that in order for this to work correctly, where recovery can occur, the client needs to start a timeout with each transmission. And if that timer pops, then the client will assume that the packet has been dropped and will retransmit. And that's what I'm trying to show here. So another name for the time used for that timeout is the retransmission timeout, or RTO. That's what that is. So this is showing that the RTO is usually larger, well, sometimes much larger than a RTT time, right? So this is an RTT time, and this is the RTO. In fact, it could be the timeout period, the RTO could be huge. And that was actually one of the early problems with TCP was its RTO was way too large. And so packet loss in the early days always occurred. And even today, packet loss within the internet, on average, it's about 1%. But it really depends on where you're at and what time it is and all that kind of thing. But packet loss occurs on a regular basis. And so when we talk more about TCP, we'll get into the issue of what is the right choice for that time, the RTO. If it's too small, then it might pop due to maybe the network becomes congested and it takes longer for that packet to make its way to the destination. The client's timer pops, it thinks the packet is lost, when in reality it's just taking a little bit longer, and it retransmits. That's bad. Okay, the other side is if the RTO is too large. So for example, if it's like a second or 2 seconds, which is roughly what TCP first used, then we could calculate the impact on the throughput, and we can sort of see it in this picture. So if the time required to send a packet when a loss event occurs is going to be an RTO plus an RTT. So throughput with a loss event. So we're still using a window of 1. So we send a message size amount of data, and now the time is going to be the RTO plus the RTT. Okay, so the throughput, so I'm going to work out a problem here. I use the calculator to compute the throughput. So I'm just going to record that before I forget it, 1.6 megabits per second. Okay, so let's say we have a scenario where our transport protocol now uses a window of 4 messages. So it's allowed to send 4 messages back to back, and then it has to stop and wait for ACKs to come back. And let's say that the round trip time is 20 milliseconds, and we'll say that the TX time is much smaller than the round trip time. That's sort of a critical assumption, which greatly simplifies things. And it's, for the most part, it's normally true. Okay, so we want to compute the throughput of this transport protocol first with no loss. So we go back to the original equation that we talked about, where throughput is found by finding the total number of bits sent per epoch divided by the time of that epoch. And so we can find the total number of bits sent. It's basically going to be a window of data. So for messages 1,000 bytes large. So we're assuming that the message size is 1,000 bytes. Window size of 4 times 1,000 bytes times 8 bits per byte. So we get the top in units of bits. The bottom is in units of seconds. So that's the time of the epoch, which is the round trip time, 20 milliseconds. Use a calculator, compute that. 1.6 megabits per second is how fast that transport protocol is going to work. Even if the underlying network, if the capacity is a gigabit per second, our transport protocol is going to be limited to this number. Okay, and now let's do this again, but we want to find the throughput. But now we're going to say, on average, 25% of packets are lost. So a loss rate over the network is 25%. And I mean, 25% is obviously making our numbers going to work out very easy, but when we talk about a loss rate, it's a statistical measure. And so it doesn't say that that 1 out of every 4 transmissions is always going to be dropped. Rather, on average, effectively 1 out of 4 will be dropped, but we might see 20 epochs go by with 0 loss, and then we might see 4 epochs with 100% loss, right? And I think those numbers sort of add up to about 25%. So with 25% loss, the way to compute this would be very similar to the formula we've used before. So the number of the amount of data sent per epoch is what we just calculated. But the time is now going to be different. We'll assume the RTO is 2 seconds. So the time on average it takes to send for a window of data is going to be an RTO plus an RTT. And so okay, so cranking that through the calculator, we get the throughput reduces from 1.6 megabits per second to 15.8 kilobits per second. So in the world of transport protocols, packet loss that involves RTO recovery is bad. And we'll look at techniques that have been proposed and used in the past, and techniques that TCP currently uses to try to mitigate the impact of packet loss on throughput.